Thanks, Nicola. Appreciate it. Should I use that mic or should I use this?
First check this one works nicely.
Yeah. Can you hear me if I do this at the back?
Seems nice.
Cool. And if I wander away, is that a problem for the video? Should I stay here?
Just stay there.
Okay,
Honestly, yeah.
cool. All right. It's easy to focus.
Not the best.
We just talked about people maybe heckling me and throwing stuff at me, so I'm going to stay still. I'm going to be a standing target, but please don't throw stuff at me. All right. My name's JP. I work at Weaviate. Just kind of show of hands, how many of you have heard of Weaviate in the past? Okay, that's a pretty good crowd. Thanks very much. So I'll be talking about databases. I know it's not seemingly the most exciting topic, but hopefully by the end you'll be like, oh, this actually is really interesting and exciting. So given that it is a database topic and it can be a little bit dry, I like to start with a few memes, right? So here's one. Vector databases are having a little bit of a moment right now. And rather than sort of me talking about it, I'd like to show people this. This is a table of vector databases that are available in the market. Actually, this is the slide of actually all the database in the market. Oh, that's not quite it either. It's actually this. So they're having a little bit of a moment, and there's a huge availability of different vector stores and vector databases right now. So vector databases are very, very popular. But why is that, right? So one explanation, and a very simple one, is AI. So this is an article from, this is already almost 6 months old, or just over 6 months old. And one explanation, you know, a simple one, is AI. But going back to that question, why does AI need a different type of a database, right? So that's a good one. And one answer to that is, of course, large language models. And I'll do a very quick recap of language models and RAG. I'm sure many of you are familiar with it, but you know, just so we're on the same page, let's do a quick recap. So large language models, we interact with it by providing what we call a prompt. And it gives us these amazing outputs. And they're these amazing, useful tools. So if I ask it a question like, hey, explain a complex thing like a vector search, whatever, like I'm 5, it'll give me quite a good answer, right? This is an actual, or snippets of an actual answer that I generated yesterday. And you know, it's actually quite a good explanation, and I probably couldn't do that much better myself. But it's not always perfect, as we know. So if I ask him questions like this, I thought this would appeal to our Dutch fans. How many world championships has Max Verstappen won? And you'll say confidently, he's won 3, which if you're a Formula 1 fan or a Max fan would know this is no longer true as of last week, right? He has 4 as of last week. So this is wrong, and that's because the information or the training data is out of date. It's got other failure modes. I can ask it things like, hey, who's this random guy, JP Hwang? And you can almost get it to say, given the model, like given certain parameters of the model, whatever you want. This is, I have this other bit that I do with listing these bios of me, and it's obviously incorrect. I am not a huge mogul or whatever. But you can get it to generate these incorrect outputs, again, very confidently and well written. But, you know, with the obvious caveat that it is wrong, which is not good. So this usage of large language models to generate these outputs is problematic because they hallucinate. What do we do about that? The currently very widely used solution is RAG, right? Retrieval augmented generation. I'm sure many of you are quite familiar with RAG. Many of you probably are sick of hearing about RAG in the last year or so. But the idea of RAG is that you don't just give it a prompt, you give it some data to augment that prompt, right? And that in turn, you ground the outputs that the model generates. And where does this data come from? Well, it comes from typically some sort of a data store. And what's important about this data store is that it contains sufficient and current data. So as you go on, and as you know, you get more and more data, and data changes, as we talked about in the example of Max and his numerous world titles, you need to store more and more data in your data store. And as this happens over time, what you end up with is kind of a needle in a haystack problem, right? So finding the right information to feed as part of your prompt to a language model has become a very important and very critical problem for having the right or having a well-functioning RAG system. And this is a key reason why vector databases have become popular, because vector search is currently one of the most effective means of finding the most relevant information to feed to our language model. In my abstract, though, I mentioned the words AI native. So I've kind of bait and switched it a little bit, right? I've talked so far about vector databases, and on the other hand, I'm now talking about AI native. So what makes it AI native? We can ask our founder at Weaviate, Bob. So Bob likes to describe AI native versus what he calls AI enabled as this. If something's AI enabled, he describes it as an added functionality. So if you can remove the AI component from that kind of application, and you lose that functionality, but your app kind of continues to work. You just lose that AI additional component. If something's AI native and you remove the AI model from that, you just don't have a functioning thing, right? You just have this broken, sad state of an application that you've removed. And that is my argument for why if you're building something with AI, you want to look at AI native databases that's built for that purpose. I'm sure you have other questions, and this is a critical one for the audience, right? I'm going to talk about why it's important, but from a user perspective, why do I care about it, right? So what I'm going to do, and what we'll do together for the next few minutes, is let's find out by building our own solution, at least conceptually, because we have like 15 minutes or 20 minutes left, and obviously we're not going to build an entire database from scratch in 15 minutes. It'd be really impressive if we could. So what we're going to do is conceptually build an AI native database, starting from scratch, and we're going to add components to it, right? Hopefully, what we'll get out of it doing it that way is to learn what these components of a vector database or AI native database does, and why, again, am I putting you through the torture of this, hey, I thought I'd be coming to a nice conference and having a chat. Why is he going to basically a computer science type talk? We get to learn a bunch of stuff. Learning stuff is cool. Don't let people tell you otherwise. The other part of it is you saw the selection of vector databases in the earlier slides, right? So the more you know about what these components do and what benefits they give you, hopefully they'll arm you with this knowledge of doing better tool selection and of course usage as well. So I'm going to go back very, very quickly and talk quickly about vectors. A vector is just a set of numbers in a very, very simple form. So it doesn't matter how many numbers there are, and it doesn't matter what precision there are. It's just a set of numbers, right? Again, why does this matter? Vectors are, at the moment, one of the best ways that we have of representing meaning. And what that allows us to do, again, this is vectors in like 30 seconds. What that allows us to do is to put objects with similar meaning close to each other in space, multi-dimensional space. And what that means is if you find these set of numbers that are close to each other, what you can do is find objects, words, images, what have you, that are similar. So that's how we do similarity searches. That's how we how we feed our language models with the right context. And that's why they are very useful for retrieval augmented generation. So vectors are cool. They're really important. We want to use them in some sort of a store. Let's build ourselves a vector store. We're going to build a database. This is like the guts of what we're doing. Obviously, we're going to have some sort of source data, and we're going to have the actual vector that represents it and the metadata that goes with it. So how do we save that? Well, you're going to want some sort of an identifier, like I'm sure this is any kind of key value store type thing, and you have a bunch of them. And this could be any kind of, key value store, right? And from a user perspective, what you're looking to do is, well, can it save the right data type? Can it save the vectors and the metadata? And if you build, a dictionary in Python, if you built any kind of like JSON data store, this is like all it is at the moment. So have we built a data store? Well, at least an effective data store. Not quite, because the thing that you want to do now is how do I find the right thing from our vector store? And how, again, we talked about vector search. So what we're looking to do in a vector store and vector search is to calculate vector similarity versus what we're looking for, right? If you want to look for the word Max Verstappen, for example, you want to find maybe similar Formula 1 drivers or Dutch drivers, that sort of thing, right? So how do we do that? The way you do it in vector databases is to compare these sets of numbers, these vectors, against your query. And you have to do it for all of your vectors in the vector store. This turns out, as it turns out, is a very expensive operation, even for the modern powerful computers that we have today. And the scale at which we're talking about these things, I'm sure you've dealt with databases before, you're talking not just, hundreds of thousands, quite often you're dealing with tens of millions, hundreds of millions and objects and so on. It's a lot, and you're dealing with floating point numbers and they're very, very long. So how do we scale this so that when you go in and perform a search, let's say you don't want to go to an e-commerce site, perform a search and wait 10 seconds for a query, right? That's no good for anyone. So how do we scale that so that when you go to production, this works well? The solution is indexes. I'm going to keep going back to the sort of traditional database land, and an index is a catalog of data. Like if you've, a slightly older person like me, I'm sure you've used physical libraries, and when you want to find a book, you don't look through every book, you look at a catalog, yeah? And that's the index, that's the same concept as a database index. It speeds up search, and they exist in relational databases already. But vectors are a little bit different. The thing is, they capture meaning. So the way we index the data is by organizing information by similarity. And of course, the clever scientists and data scientists among us have come up with different ways of doing this already. And you'll hear about different vector index types as you go. The main thing to remember about these, though, is that they are, most of the time, approximate, right? So what you're making is these trade-offs between speed, search quality, and so on, and resource usage, typically your memory footprint. So the simplest form of an index you might have is what's called a flat index with very little overhead. And it really is just brute force search through all of your data one by one by one. And this is great. It's like low overhead, it's relatively performant for small sets and so on. But once you start to have more data, it obviously slows down, right? If you have 100 times as much data, it's going to take 100 times as long, which is not really going to work for you. So the current typical solution is a graph-based index. And the most common type out of those is what's called HNSW. And don't worry, I won't go into that too much. This talk is probably deeply technical already. And the main benefit of this is that it's extremely scalable. And the typical downside of this is that its memory footprint is relatively large. So let's come back to that a little bit, but I'll talk at a very high level, like someone like me who prefers high-level things might understand. So HNSW is a set of connections of these vectors. You can think of it as like multi-layered graph. So at the lowest layer, all of these nodes or the vectors are connected to each other by how similar they are, right? So you can go from one to its neighbors and perform your searches from that level. But this can be, a little bit cumbersome. So what you want to do is go up to higher layers where you have subsets of nodes. And by doing that, you build these shortcuts between regions of similarity or similar things. So you start at the top and you perform your searches from there onwards, and you drill down to the closest neighborhood. It's a little bit like, if you're using Google Maps to find a near area, you don't start from like a very zoomed in area, right? You kind of like look at the world and go, oh, I want to look for something in this area, zoom in a little bit, zoom in a little bit. It's conceptually like that. If you're a little bit more computer sciencey, it's like a multi-dimensional skip list is a good intuition if you understand that. So, anyway, what is HNSW? It is an in-memory data structure, which is kind of critical to where we're going with this. So a typical limitation is the memory footprint. And what takes up all this space? Well, it takes up a certain number of connections. That's not that big. But the thing that's going to take up a lot of memory is how big those vectors are that we're going to load into memory. So each vector is like a floating point number, so it's 4 bytes or so, exactly 4 bytes. And if you have 2,000 dimensions, you're actually looking at 8 kilobytes per vector. And remember, we're talking in a database context, not just hundreds of thousands, not just single millions, but quite often hundreds of millions and so on, right, of rows. So if you have 10 million objects, you're going to need 65 gigabytes of RAM, which is already a lot. 100 million objects, you're going to need 650 gigabytes of not storage, RAM, memory, and it's going to scale so on and so forth. And that's just for your vectors and your vector index. I don't know about you, but my computer is not going to support that, right? It's like, I don't know how many of you have laptops with 600 gigabytes of RAM. So there's solutions to this that these data scientists have, again, come up with. So there's the idea of quantization. You might have heard about quantization, of course, in the context of models, right? We talk about language models that are quantized in a particular manner, but you can also do this with individual vectors as well. So that reduces the precision to integers or binary. And I won't go into details of that too much, but here's the impact of doing that. If you have a normal HNSW graph at like 1 million objects, and this is not a benchmark, this is just me running some experiments on my laptop. At about 1 million objects, I'm using 6 gigabytes or so of RAM. If you apply quantization, that actually goes down by 2/3 or so. And I talked about the flat index, which is more efficient. It can go down even further. Remember we talked about, the footprint of 650 gigabytes of RAM at 100 million objects. And this isn't some sort of theoretical case that I'm, bringing up, because we have users that use billion plus objects, and we're talking literally requirements of terabytes of RAM. What does that mean in real terms? Well, here's a spot instance pricing for AWS that I looked up a couple of weeks ago. If you want an instance, and they have the same number of CPUs, right? If you want an instance with a terabyte of RAM, it's like $7 an hour US. But if you now halve that requirement for a similar instance, you're looking at, what's that, like 40% of the price or so? $6 an hour doesn't seem so bad. Like, obviously you wouldn't, if you get paid $6 an hour, that's terrible. But what's that translate to yearly usage? Well, you're looking at about $60,000 per year. Again, that going down to $20,000 or so a year, just to run your instance with enough RAM. And just by turning on quantization, this is the kind of financial impact that you'll have to your usage. And that's why it's so critical that you think about how you manage RAM requirements when you run a vector store. So from your perspective, what's really useful to know is that there are these different types of indexes available, and you have these options that I covered. I know very, very briefly in terms of tuning speed. I didn't talk so much about search quality, but obviously when you have quantization or some form of compression, there's usually some form, slight loss in recall or search quality, so that's another thing to think about. But of course, your memory footprint and resource usage and the financial implications or costs associated with that. I talked about indexes in terms of like different index types, but also I very, very briefly mentioned that there's a keyword or traditional indexes. And what a vector database gives you is that because now you have 2 indexes, you can do some like filtering. So you can now not just perform a vector search, you can also perform filtering and say, oh, I don't just want to search for, Max Verstappen, but I want to search for Max Verstappen in my library of articles that are just from Wikipedia, right? So that's like a neat thing you can do, and that's only possible if you have 2 indexes, one of which is a vector index. And all of this needs to happen at speed. At this kind of scales, speed becomes really, really critical. So, people apply different types of concepts to it. So one really interesting one is something called roaring bitmaps. And that data structure is applied to perform fast filtering that happens with, that you can apply to different distribution of data, basically. So that's kind of a fun thing to look up if you're into, a little bit of data science nerd stuff. Another cool search method, which you might not have seen before, is hybrid search. And that allows you to combine keyword search and vector search results. Under the hood, each search uses a different index, right? So you use the same query, perform a hybrid search, perform a vector search, perform a keyword search, and you join these search results together to have a combined list. And in practice, this tends to be the search type that's used most often by our users. Cool. Okay, so it's been, spent like 10 minutes building our database. We've done a lot, so let's have a look back. We've got a data store with different types of indexes. We can store these objects and so on. We can now perform searches. We can do filtering, and we can return a set of results to our users at speed. So we've done really, really well in just, a few minutes of time. Now, So it gives us a mini database where we can store data and whatnot, but it doesn't scale all that well. So what happens if you have that and add more data, if you add multiple data sets and so on, what do you do? The solution is to treat this as one small database. So now the trick is, can we multiply these and have not just one mini database, but multiple sets of these? And now we can do things with it, like have them distributed across multiple devices. And in traditional database land or distributed database land, these are called shards. And this concept applies similarly to vector database as well. But this is a really important aspect of how you might scale, because the operation of sharding in vector database is a little bit different. And you want, of course, to have a database that allows you to apply to have sharding and so on. And this solves a lot of issues. So in short, each shard can be part of one collection that gives you horizontal scaling. And in a vector database, what you can do then is have searches go to different shards, and you simply combine the results. You can also have shards that are cloned, right? And this is the idea of replication in a distributed database, which I'm sure you've seen before if you're in database land. And then you coordinate the database schema, make sure each one of those are actually identical, and deal with all the fun of, distributed database challenges in computer science. But the main thing is they allow you to keep the objects consistent, and if any of the nodes go down, then you have redundancy and robustness and resilience. Cool. So now we have a bunch of shards that have object stores, vector index, inverted index, and so on. How do we get even bigger? Well, what you want to do is have multiple shards that can also talk to other nodes. And you want to apply compression techniques and so on. So what you end up with is a system that looks a little bit like this, where each of those shards look like the expanded diagram on the left. And you might have replication, which are represented by the same colors, and distributed systems like so. And of course, you can deploy them on all sorts of hyperscaler infrastructure. But there's another thing that's very, very useful for AI native or vector databases. And that's the question of, hey, I talked a little bit about vectors and said they're really important. Where do they actually come from, right? If you've generated vectors before, you might have gone through these steps of obtaining embeddings yourself. And you might use some sort of provider like Cohere and so on, provide your objects and get your vectors. But this is kind of, one of those things that are necessary, but not the most exciting thing to do. It's a bit of overhead as a developer. And what you want to do really is use those vectors for searching, for building a database and RAG pipelines and so on. So what if you could have your database obtain the embeddings for you? And with certain databases, like Weaviate, you can do that and have embeddings obtained in the background. And you can, of course, ingest data with embeddings, but what you do with these provider integrations, if you don't provide your own embeddings, is that your integrations can contact your favorite model provider like Cohere, Google, AWS, so on and so forth. And what you end up getting is a system with a vastly simplified experience where all you do as a user is just send data back and forth to your database. And all this embedding stuff is just under the hood. And it just kind of happens for you. And that's a vastly improved user experience because it's a little bit like, no one deals with assembler code or assembler anymore, right? It's like you want to deal with stuff that adds value to you. So when you perform a query, again, you're dealing with just queries and returns and so on. So what have we built so far? We've built an object store. We've added these indices, and they can store our indices, perform all these searches, filtering, so on. And now we have scalability through our replicated shards, and we can deploy them through different hyperscalers. And really a key thing is, another key aspect like I talked about is these integrations with model providers, whether they be generative models, vector embeddings, and so on. And that's our system right there at the end of the day. And we talked at the start about what is AI native, right? And in terms of if you take AI models out of the system, how much of this would work? And the answer is not very much, because the concept of vector embeddings is very integral to this system, and the integrations with not just vector embeddings, but also generative models is very, very critical there as well. So that's it from me. I do realize I went through all of that fairly quickly, but hope that was useful as an overview of architecture of what makes AI native or vector databases different from your traditional databases. If you do want to try out Weaviate, I do encourage you to check out the QR code and go to Weaviate, where you can try out cloud-based instances and so on. And of course, I am here for questions and for at this moment and also after.
Wow, what a talk. Usually, whoa.